Economics gives us models. Econometrics gives us answers. Theory often tells us the direction of an effect. More education should raise earnings. Growth should improve living standards. But policy requires more than direction. We need to know the size of an effect, how certain we are about it, and whether what we observe is actually causal. That is the role of econometrics. In this first episode, we define econometrics, introduce the basic model, compare the main data types economists use, and explain why causality is the central challenge of empirical work. At a basic level, econometrics means applying statistical methods to economic data. But that short definition hides an important distinction. Theoretical econometrics develops the tools, estimators, tests, asymptotic results, and the assumptions under which those tools work. Applied econometrics uses those tools to answer concrete questions. Does a minimum wage increase reduce employment? Does another year of schooling raise wages? Does foreign aid increase growth? Econometrics is the bridge between abstract theory and measurable evidence. This bridge matters because economic theory is often qualitative before it becomes quantitative. A model may tell us that one variable should move up when another changes, but policy decisions require more than sign predictions. Suppose more schooling raises wages. By how much? Suppose a minimum wage increase helps low-wage workers. Do the wage gains outweigh any job losses? Econometrics turns qualitative reasoning into quantitative measurement. It asks not only whether an effect exists, but how strong it is and whether it is estimated precisely enough to support decisions. The basic language of econometrics is the econometric model. A simple example is wage equals beta 0 plus beta 1 times education plus u. Beta 0 is the intercept, beta 1 is the slope parameter, and u is the error term. The slope tells us how wages change when education increases by 1 unit, holding other relevant factors fixed. The error term collects everything we have not explicitly put in the model. We write down a relationship between an outcome and explanatory variables, then use data to estimate the unknown parameters. That brings us to the importance of parameters and the error term. The parameters are what we care about, but they are unobserved. We never see the true beta in the population. We only estimate it from a sample. The error term represents all the omitted forces affecting the outcome. In a wage equation, it may include ability, motivation, family background, or local labor market conditions. If one of those omitted factors is correlated with education, the estimated schooling effect will be biased. The kind of data we have strongly shapes the econometric method we use. Cross-sectional data gives us many units observed at one point in time. Time series data tracks one unit across many periods. Pooled cross-sections combine different samples from different years. Panel data follows the same units across time. These structures are not minor details. They determine which assumptions are plausible and which tools are appropriate for estimation and inference. Consider the contrast between cross-sectional and time series data. In cross-sections, the main benchmark is random sampling. We hope each observation is an independent draw from the population. In time series settings, ordering matters. Today can depend on yesterday. Inflation this month is related to inflation last month. Output growth can be persistent. So methods designed for independent observations often break down in time series. Before we estimate anything, we need to understand what kind of variation the data is giving us. Panel data is especially valuable because it lets us observe the same unit repeatedly. That structure can help control for time-invariant unobserved factors. If a worker has high innate ability and that ability does not change much over time, panel methods can difference it out or absorb it with fixed effects. The same logic applies to firms, schools, or countries. Panel data often gives stronger leverage for causal interpretation than a single cross-section does. Causality is the central challenge in econometrics. If two variables move together, that alone does not prove that one causes the other. The direction of causality may run the other way, or both variables may be driven by a third omitted factor. This is why economists care so much about Ceteris Paribus reasoning. We want the effect of x on y holding all else fixed. In observational data, that is hard because all else is rarely fixed by design. The ideal benchmark is a randomized controlled experiment. If treatment is randomly assigned, then on average the treatment and control groups differ only in the treatment itself. That means differences in outcomes can be interpreted causally. In many economic settings, ideal experiments are impossible, unethical, or too costly. Even so, the experimental benchmark is useful because it clarifies what observational methods are trying to approximate. To make this concrete, consider the Dollar and Kraay study on whether growth is good for the poor. They examine whether the incomes of the poorest fifth of the population rise when average income rises. Their estimated relationship is poor grow equals minus 1.25 plus 1.31 times mean growth plus an error term. The key coefficient is 1.31. A positive slope tells us that when the overall economy grows, the incomes of the poor also rise. This leads naturally into the classical empirical methodology. First, state the question clearly. Second, specify a theoretical or empirical model. Third, obtain data suitable for that question. Fourth, estimate the parameters of interest. Fifth, test hypotheses and evaluate significance and economic magnitude. Finally, apply the results to policy, forecasting, or theory refinement. Econometrics is not one isolated calculation. It is a workflow for disciplined empirical reasoning. To summarize, econometrics gives economics a quantitative language for evidence. It helps us define models, estimate effects, distinguish correlation from causation, and evaluate policy claims with data rather than intuition alone. We have introduced the econometric model, the main data structures economists use, and the causal benchmark that motivates empirical design. In the next episode, we turn to simple linear regression.